Classifying chemical reactions post-lab. So the main part of this lab objective was to start working on figuring out the 5 types of reactions and how to predict the products of those reactions. We had to look for observations and details. This slide here has lots of good information on it for y'all, including one of the things y'all struggle with, which is AQ. Most of the liquids that we work with in lab are going to be classified as AQ because I make them the same way you make Kool-Aid. I put the solid in there and then I fill with water. The only liquid that we should have is H2O in our labs. Notice that liquid has to be a pure substance. This also gives you the 5 types of reactions, and I have some more slides in the back that also emphasize this as well. So hopefully on the pre-lab you figured out that you're working with flammable things. You obviously need to be paying attention, tie your hair back, keep your area clear of flammable items, that kind of stuff. So you did your procedures, and now let's look at these reactions. So the first one, I asked you guys, why does it burn? And many of y'all could not tell me. So when we say something burns or combusts, we mean that it has water. I'm sorry, when we say they burn or combust, it means that oxygen is present. Okay? And that's what we're looking at. This is actually an inorganic combustion. So many of y'all figured out that you're starting with solid magnesium. Eventually you figured out the O2 gas, and then you did your crisscross and you figured out that we produce MgO. I also like the fact that when I asked some of y'all, well, how do you know it didn't melt? You told me because it went from solid to solid. Absolutely. So the second reaction, you took magnesium and you placed it in HCl. And many of y'all measured your temperature and noted that it increased in temperature. It was what we would call an exothermic reaction. So it gave off heat, right? Some people use universal indicator to put in there. It sometimes helps you see the bubbles better. They notice it changed from red to kind of an orange, and that's good. All these are clues. And then you were supposed to take your wooden stick, catch it on fire, and put it into the neck of the test tube. And you'd hear a pop. And that pop tells us we have hydrogen gas and not oxygen. So we use all those clues to figure it out. Okay? And so simply we have Mg plus 2HCl aqueous yields MgCl2 plus H2. Okay? And that's a single replacement reaction. And then you took the ammonium carbonate and you guys put it in the test tube and you gently heated it. And so if you really want to mark that we gently heated it, we'll put a triangle on there. That triangle tells us that we have heat. And that heat is a catalyst. You've heard this in biology. So the catalyst is there to assist in the reaction, but it doesn't make it go. It's not involved in the direct reaction. It just helps make it happen. So when you get done, you put your litmus paper in there and you discover that your red litmus paper turned blue, which indicates that we have a base, and that base is NH3. Some of y'all might also know that you had a smell, and that's also evidence. And then we just had to logically start looking at what we have. We looked at the neck of the test tube. We know that we have H2O, and then obviously we have C left over, so the other gas is carbon dioxide. So some of this we're just taking clues. So then we have a double replacement reaction. We have the calcium carbonate and the hydrochloric acid. So the calcium carbonate was a solid, HCl is an aqueous. Not all double replacement reactions will be aqueous and aqueous. So just in this one, we see that we have a solid with an aqueous. That's a double replacement reaction. we're looking that everybody has a partner. So everybody has a partner, okay? And again, we have to look for clues of what's happening. We get a gas that's being produced. We stick the splint in there. It does not grow any bigger, so it doesn't ignite stronger or anything. It actually goes out. Many of y'all tell me it goes out, and that's going to be indicative of carbon dioxide. And again, we look at the neck and we see that we have water droplets growing there, and that's H2O. Single replacement reaction, so y'all took zinc with the copper chloride. And we've done this before where we get that reddish precipitate out, that's your copper. And then zinc goes into solution, becomes zinc chloride. We also notice that we have a color change between when we start and when we end. We have another double replacement reaction. We have copper chloride and sodium phosphate. We notice that there's a solid precipitate formed, and we have to kind of figure out what that is. We have a chart that actually tells us about solubility, and it's going to be the copper to phosphate. That's going to be our solid that's being produced. Sodium chloride is the other product that would be produced, and hopefully most of you know that sodium chloride is dissolvable in water. The last one, reaction number 7, is also another double replacement reaction. It's an acid-base reaction, which is what we do a lot of in the spring. We have sodium hydroxide and HCl, and it produces a salt, which happens to be on this reaction, NaCl. That's also aqueous. And then we also have H2O, which is our one liquid that we're producing. So those are your reactions. And I know I talked with some of y'all about this. What law do we follow when we're working with chemical reactions? We have to follow law of conservation. So whatever I start with, I have to end with, which is why we have to balance it. So we have to make sure that the left side equals the right side, just like you do in math. Okay? How can you tell the difference between a single replacement and double replacement? I'm looking for partners. Does everybody have a partner? If there's somebody by themselves, then I probably have a single replacement reaction. Periodic table, because that's always good to review. Law of conservation in math, I just pulled up some diagrams to help you with that. We just can't just pretend like fluoxetine exists and explain it that way. It actually has a reason for what it's doing. It's a law of conservation, but remember, law of conservation, we can clearly see when we have a closed system. If we don't have a closed system, we can't exactly claim it, but it is our guiding principle. And this is going back over your naming, nomenclature. Again, reviewing ionic and covalent because you're still working on strengthening your skills on that, as always. And there's your type of reactions as well. And I also reviewed you over exothermic and endothermic. And then bond making, bond breaking, intermolecular forces, that's what's holding everything together. And more intermolecular forces, just trying to get you to think about, well, why is it holding together and other times it's not. And that is your post-lab. Make sure you write all your answers in and complete your standard 5 post-lab. Great job. Live long and prosper.